Okay. Are we on?
Yeah.
We're good? Okay, now. Fluid dynamics and statics. All right. Let's go over some key points. First thing I want to go over is simply, solely, specifically, and only a definition. Just a definition that you will come to appreciate and embrace. Okay. It says we're looking at the buoyant force. Now I'm cheating a little bit because we've done this already and it's a little bit of a review, but let's say we have water and I immerse something in water, completely the bottom of the tank. And that object is going to displace fluid, correct? Okay. You know as well as I do when you've gone swimming or you're in the pool or whatever, the weight of something heavy is less when you're in the water, correct? Yes or no?
Yes.
Okay. Now, if that's true, why? Why does it weigh less? And the reason it weighs less is because the buoyant force. The weight is going down. Can you see it here, guys?
Yes.
This is the weight of the object. The weight of the object is going downwards. In other words, if I drop a stone in water, it's going to sink. It's going to sink because of its weight, correct?
Yes.
So it's going to sink. So the weight of the object is always towards the center of the earth, just like always, right? But now you have something called the buoyant force, which acts contrary to that. It acts contrary to the weights. Yes? Now, how do I actually measure? How can I scientifically measure the buoyant force of something? And I'm going to demonstrate this in class. It's actually easier than you think. Okay? I could actually, no, I'll do it in class tomorrow. The buoyant force, let's read what I have on the board together, okay? It says, I'll come off camera so you can hear my voice. The buoyant force, F sub B, is the weight of the volume of fluid displaced by an object that is in the direction opposite to its weight. The difference between the weight and the buoyant force is equal to its apparent weight in the fluid, or simply FW minus FB equals FAPP. All right? You all right with that? Okay. So, it's simple. I have a giant battleship. Giant battleship. Giant. Okay? And it's going to be sitting in the water. That's the ocean. And here's my giant battleship. Right? Now, is that giant battleship sinking? Is it rising? It's just staying right there. It's just staying right there. It's not going up or down, right? So let me ask you this. Is there a net force up or down on that battleship? Now, it may be sailing through the ocean, whatever, but in the up or down direction, in the vertical direction, is there a net force on that battleship? Is it sinking? It's zero, right? It's zero, right? Yes or no? So if it's zero, If it's, can I erase this now? Can I erase this? So if this battleship, if that battleship has no apparent force, no external force on it, no external force, no net force in the vertical direction, what can you say about the relationship between the buoyant force and its weight? They're equal. So this is the battleship. The battleship looks like this. Right? So the buoyant force equals the weight. Yes? So think about it. The volume of water that battleship displaces equals its weight? Yeah. It has to be. Because there's only two forces that work here. Vertical forces. There's the downward force, which is the weight, and there's the upward force, which is the buoyant force. So if it's not moving vertically, then there's no net force vertically, right? So if there's no net force, they must be equal. Would you agree? Yes or no? So something that floats, these are equal, right? Something that sinks, which one would be greater? The weight, right? So this is floating, right? If something's sinking, it would look like this. Would you agree? This is sink. Right? That's sink. Yes or no? Okay. If something is rising, right? Can I erase the boats? It would rise, correct? Would you agree that that's correct? So you have floating, sinking, or rising. Yes? All vertical. And that's the relationship between buoyant force and weight. Yeah. Let's do one more thing before we quit, okay? All right? Now, look up, don't stop it, but look up the density of gold, aluminum, and iron right now.
What?
The density of gold, aluminum, and iron. Can I erase this now?
Yeah.
Is that all right? Gold, density of gold, aluminum, and iron. Three elements. What are they? What's the density? Anybody?
I'm looking for economics.
We'll say this again?
I'm looking for it.
Okay, take your time. Come on, hurry up, take your time, take your time. Just say density gold, that's all.
That's for gold.
Gold, yeah, but I want to see you all three, but just give me gold. What do you got, dude?
Smoothie.
Loading. I just want a relative number.
It's for another.
What do you got? Wi-Fi slow?
Yeah.
Okay.
Gold is 19.3.
19.3. So this is 19.3 grams per milliliter, right? And what is it in terms of, let's say, instead of saying milliliter, let's do, what is it in terms of, when you talk about density, the unit labels are kilograms per cubic meter. What is it in terms of kilograms per cubic meter? I mean, I can tell you myself, I suppose.
Kilogram and liter per
It's going to be 19300, correct? Right? Kilograms per, is that correct?
liter.
Right? Okay. Did you look it up?
I have the rest.
You have the rest? Okay, what do you got for aluminum?
Aluminum is 2.7
Grams, okay.
grams per
0.7.
centimeter
Cubed,
cubed.
0.7 grams.
Per centimeter cubed.
Okay, and what's iron?
Iron is 7.874 grams.
All right, 7.8, is that right?
7, oh yeah, sure.
7.8
Yeah.
grams
Per
per.
centimeters cubed.
Now make sure you look it up. Densities, kilogram per cubic meter, just like that. Put that right in your calculator, in your phone. Densities of elements, put in this. Densities of elements, kilograms per cubic meter, just like what I just said. Densities of elements, kilograms per cubic meter.
Aluminum 2.79.
Right? Are these right?
Yes.
Right? Yes?
Yes.
What do you get? May I see it? Yeah, it says aluminum says 2.6 here, or it says 2700, 2600. It's really incorrect. You should put this on. Yeah, let's go. That's about what we said, right? Yeah. Okay. All right. So this is what I want to do. Okay, you ready? Okay. Here are the densities. You can see that aluminum is least dense. Now remember, just for your own edification, density of water okay. Can you see that? Can you see that? Yeah? My videographers, I love it. Excellent. All right, so gold is most dense, makes sense. Then aluminum is least dense, makes sense. And look at aluminum. It's only 3 times more dense than water. It's not very dense, really, is it? It's not. And then iron's in the middle. Okay, easy? Okay, so everything all right, big guy? Okay, so this is my question. Are you ready? All right, Sandy, I need your assistance. Okay, I need you to point it down on these books. Can you see the books?
Yeah, we can
Okay,
see
now,
that.
I have SAT review books. Okay, good. Now, commercial. Okay. Volume. Okay. Now, right what I have. Gold, aluminum, iron, right? Very heavy, very light, in the middle, okay? Right? You okay? Now, which book has the greatest buoyant force?
They're all the same.
Yes! They're all the same. Why are they all the same?
They have the same volume.
They all have the same volume. Remember, buoyant force is the weight of the volume of water displaced. Clear?
Yeah.
So they're all the same. Okay, now, next. Now, I'm making this up, you know that, right? Okay. 1 kilogram of gold, solid gold. It's probably more, but I'm just trying to make a point. Gold, okay? Iron, 1 kilogram of iron, right here, right? It's probably more, I know, just bear with me. Aluminum, okay? 1 kilogram of gold, right? Does that make sense? Smallest, largest, 1 kilogram of aluminum, and in the middle, right? Which one has the greatest buoyant force?
Aluminum.
Aluminum, why? Because it is the largest volume, correct? So what's the weight of the aluminum? The weight of the aluminum is, the apparent weight is going to be what? The weight of the aluminum block minus the weight of the volume of fluid it displaces, correct? Yes or no? You with me? Good. Easy? Good? I'm done. Am I done? Good? Finished.